course, he needs no introduction to this audience. He's going to talk about novel pathways to fuels and lubricants from biomass. So, Alex, the floor is yours.
It's there. Try to use the modern techniques here of putting the pointer on the slide here. So thank you. Good morning to everyone. I appreciate the opportunity to come and talk to you about the work that we're doing in biomass conversion. And I'd like to start out by motivating this talk with a few slides and say, why are we interested in biomass conversion? And if we go to the next slide, the picture is clear here in this cartoon. So if you look at this cycle over here, starting on the left, the idea is to find a renewable, sustainable source of carbon that can be converted into hydrocarbon or close to hydrocarbon type fuels that can be used for a variety of transportation purposes. And so the basic idea is that we'll let nature take CO2 from the atmosphere, take water from the ground, combine this to make a carbohydrate, so characterized by a CH2O unit over here, and that will then grow as either a grass or some sort of a tree, wood, that can be harvested, converted into fuels, burned for purposes of transportation, and the CO2 goes back in the atmosphere. And the reason that this is sustainable is basically we're recycling the CO2 from the atmosphere. Now, this is a nice concept, but there are a number of boundary conditions that have to be met. We have to make sure that there's a minimum of land usage so that we're not competing with land for agriculture. Irrigation becomes an issue. You'd like to work with plants that require minimum water, if possible. There has to be, at the end of the day, a net savings in the CO2 emission relative to fossil fuels, because if that's not true, then we're not gaining much by introducing what you'll see as a complex new technology. And notice that there is oxygen in carbohydrates, and that needs to come out in order to increase the fuel value of the product. And so we need a source of hydrogen, and I'll talk about that in just a moment. The reason this problem is complex, and we're all highly challenged to carry it out in various ways, is that Mother Nature didn't make the plant material look anything like a liquid fuel. And so at the top of this slide, you see an image of plant walls. On the right is a cartoon of the various components. You can see where the cellulose is. It's in crystalline material, wrapped up with hemicellulose and surrounded by lignin. And the average composition of this material is CH1.8O. And you'll notice that that's quite different from CH2, which is the average composition of transportation fuels, be they gasoline for automobiles, jet fuel for aviation purposes, or diesel for trucks. So the challenge is to put the carbon number in the product in the range of gasoline, jet, or diesel, and to remove as much of the oxygen as possible. And if you think simply in terms of stoichiometry, removal of oxygen can come by sacrificing carbon as CO2. So if this is green carbon coming from the plant matter, that's okay, because that's the same kind of carbon that you harvested from the atmosphere. The other way to do this would be to use so-called green hydrogen. In other words, hydrogen derived from a non-carbon source. And the only one we know of is water. And so you'd have to have a very efficient way of electrochemically splitting water. But today, mostly it's rejection of carbon as the method. So here is a nice outline prepared by George Huber and Jim Dumesic a number of years ago of what are the alternatives. So you start on the left with cellulosic biomass, and on the right are the desired products. And so I'll go through this slide to tell you how we arrived at the strategy that we finally used in the work that will be the balance of this talk. So if you start at the top, one possibility is to take the biomass and simply steam reform it to make syngas, clean that up exhaustively to get rid of all trace elements and impurities there, and then do Fischer-Tropsch synthesis, methanol synthesis, water gas shift, chemistry if you want hydrogen, and this is all done by chemical catalysis. So recent analyses show that this works only if you can do it on a large scale. It's economical on a large scale. But the CapEx, the capital expenditure, is high. And most of that is tied up, roughly 70% is tied up with generating the synthesis gas, and then 30% is tied up with converting the syngas into products. The second alternative is to go to the bottom of this slide and do pyrolysis in the absence of air. This produces bio-oils. These are highly unstable materials which need to be hydrogenated, and that can be done, and then you can get an intermediate product that could be blended with petroleum and then refined in the same way that petroleum is, or could be refined separately. The recent analyses show that this is feasible, but the liquid yields are low to moderate, and the most critical thing is that there's a high demand for hydrogen. And right now, that source of hydrogen is conceived of as methane. So this adds a black footprint on top of a green process. Now, what we're left with in the middle is first of all, the traditional way of doing things. You take the cellulosic biomass, you pre-treat it, and then ferment it to make ethanol, butanol, in some cases alkanes. Here's a schematic showing what you might do. So you pre-treat the plant matter with dilute acid, dilute base, a variety of ways to release the lignin from the carbohydrates. Then you have to break down the carbohydrates. This is usually done with enzymes to produce the monomer sugars, which you then can co-ferment to make mostly ethanol, but also more recently butanol. Now this works, and it's fairly advanced, so we have some economic numbers here. And the most recent numbers say that if you were to make the equivalent in terms of energy of a gallon of gasoline in the form of methanol, it would cost $3.27. But the killer is, why this is so difficult and why it's not being implemented more broadly, is the expense of the enzymes. Half to more than half of the price of that production is tied up in the enzymes, and these are largely throwaway catalysts. There's also a significant tie-up of money in the pretreatment process and then in the separation process downstream. So this is what's led our group to think about the following scenario. So we imagine ourselves in the Amazon in Brazil. We're harvesting sugarcane. There's the tractor there showing the sugarcane harvesting. The cane is milled into small pieces. The sucrose, roughly 10% by mass of the sugarcane, is extracted to make sugar. We're then going to either dehydrate or ferment this material, but shown here is the dehydration, to make 5-hydroxymethylfurfural. And the bagasse, which is the byproduct of the sugar extraction, will take the easy part of that material, the hemicellulose, and release that as xylose. We can dehydrate the xylose to make furfural. And so the hydroxymethylfurfural and the furfural, together I'll refer to them as the furanics, then become the building blocks. The alternative to this is to ferment the sugar to produce acetone, butanol, and ethanol, the so-called ABE process. So, to summarize, the strategy is to start with the sugarcane on the left, over here. We're going to release the sucrose, sugar, combination of fructose and glucose, break that down into the individual sugars and dehydrate them to HMF. Or And we will take the hemicellulose in the bagasse, break that down. That's fairly easy to do with dilute acid to release the xylose, and then dehydrate the xylose to make furfural. And the alternative is not to dehydrate the glucose, but to go and ferment that into the so-called ABE mixture shown at the bottom of the slide there. So the first step here is dehydration. Now here again, nature isn't kind, although in principle this is an easy process to go from, say, xylose to furfural, the chemical shown in the green box here. There are processes that lead to intractable, soluble and insoluble products collectively referred to as humans. And this happens both directly from the xylose, directly from the furfural, and as a mixture of the furfural and the xylose reacting together. Now, we've looked at these kinetics and we've found that most of the humans, the undesired products, come from the co-reaction of furfural and xylose. To catalyze this overall process, you need two types of catalysts. The dehydration is facilitated by Bronsted acid, but if you isomerize the sugar first, the xylose, to either lysose or xylulose, the two compounds shown on the bottom here, and make an isomeric, equilibrium mixture of the two, it turns out that the xylulose, isomer of xylose, dehydrates much more rapidly than does xylose by itself. And that chemistry, the isomerization, is promoted by Lewis acid. There's a similar chemistry, I'm not going to show it, for glucose, and the only additional thing is that the Bronsted acid will facilitate the rupture of the hydroxymethyl furfural into levulinic acid and formic acid. So there's further chemistry that goes on to the right here. Now we've been able to carry out this chemistry using tin chloride, which is a material which hydrolyzes in water, as shown here near the red dot, to produce tin cations, which are hydrated, and protons. So you're making Lewis acid and the Bronsted acid in situ. And they work together very nicely to isomerize the xylose to the various products. And then to minimize the human formation, we're extracting the products, the furfural, the product, I should say singular, into toluene, but we can also use other solvents. And so on the right is shown that we can get up to 85-90% conversion of this single sugar using this mixed Lewis acid, Bronsted acid catalyst. And at the same time, we can get up to 85% of the selectivity of 85% of the desired product, which is the xylose. Now we can also use a combination of solid catalysts, heterogeneous catalysts. So tin beta is one that we have used effectively for this chemistry, and amberlist 70, a solid acid. So these together will give you roughly the same results. And the same can be done starting with glucose. We isomerize, in this case, to fructose, and that's absolutely necessary because fructose then dehydrates very rapidly to HMF. And the HMF, it's not shown here, will undergo further chemistry to make the levulinic acid and the formic acid. And so if you look at the upper panel over here, you see the same kind of trajectories in time for tin chloride as the catalyst. And if you think of levulinic acid here and formic acid as having come from HMF, and you add that in summary, then you get, again, roughly 85% selectivity to the desired products. So now the question is, if you've made the compounds I'm showing in the red box over here, furfural and hydroxymethylfurfural, what can you do with them? And this is an overview slide that shows that there are several things that you can do. You can put them together to form these trimers by combining the furanics through their rings, the furanic rings, and then hydrogenating them to make these tetrahydrofuran derivatives. This, as I'll show you in a moment, the chemistry, is a desirable product for diesel applications. It has an energy density of 34 megajoules per liter, which is comparable to commercial diesel, and a cetane number of 60. So anything with a cetane number of over 40 is actually a very good product. The way we would make this is to do the trimerization using a solid acid catalyst. Now, we've looked at many, including zeolites and other solid acids, but the best one we have found is to take toluene sulfonic acid and graft it onto a surface. So here in the cartoon, you're seeing silica, the surface of silica, with an alkyl, sulfur alkyl linker to the sulfonic acid group. And this works extremely well. We can get 65% conversion in 2 hours. We can get nearly 100% conversion in closer to 6 hours. And by this means, we've made all the compounds that I'm showing you on the bottom of the slide. And this is was a featured article in Chem. So once you've made the saturated compounds with the furan ring there, you want to reduce them. And we have found that a very active catalyst for doing that are palladium nanoparticles. The cartoon here shows one of these. These are about 1.5 to 2 nanometers across, as seen by TEM. And they're surrounded by little hairs, we refer to them, which are alkyl groups, which have in the middle an ionic liquid group. So this is an imidazolium group. It's hard to see, but this little red object is imidazolium. And it depends, the selectivity of this catalyst depends very much on what the counter anion is. And the best one that we have found for promoting the reaction that we're showing here to get all the rings saturated but none of the oxygen taken out is BF4-. And we believe that the reason that this is an effective catalyst is that the hairs, or this hydrocarbon environment, is oleophobic and kicks out the intermediate product, the cyclic ethers that I'm showing over you here, before they can undergo further hydrogenolysis, opening up of the tetrahydrofuran rings. And by keeping the hydrogen consumption low, we reduce the hydrogen required for this chemistry by 55 to 60% relative to going to, for example, the 6-alkyl undecane that I'm showing on the left. Now, let me come back to the overall picture, and we'll treat the last combination, which is the one shown here on the right. And here the basic idea is going to be to open up these furanic rings, I'll show you how in a moment, to make ketones. These are methyl alkyl ketones. And these can be combined then in various ways to make everything from jet fuel to lubricants by adjusting the molecular weight. Go ahead here. So the way we do this is to do a hydrogenation, and shown here on the upper left. So HMF to 2,5-DMF, the dimethyl furan, and then you can open up that under further hydrogenation to make the 2-methyl hexanone. This is best done with a palladium carbon catalyst. You can do similar thing with furfural, and you make the 2-pentanone. You can also make the 2-butanone, but by a more indirect route, starting again with furfural. The alternative is a biochemical pathway to these ketones, which is to take the sugars and ferment them to 2,3-butane-diol. And you can do this with yields of 200 grams per liter. That's very high yield. And it's a very easy dehydration then from there to make the 2-butanone. Or alternatively, you can do the ABE fermentation to make acetone, butanol, and ethanol, and then do Verbet coupling to make 2-pentanone or 2-heptanone. So the compounds that are in the red boxes are what I'll refer to as synthons. And we'll see that in a moment that they're very flexible, and I can combine them and oligomerize them, either dimerize them or trimerize them in various ways. So what I'm showing you here is illustrated with 2-hexanone. So we start at the top left over here, 2-hexanone. And in the presence of either an acid or a basic catalyst, the base being represented by calcined hydrotalcite, the acid by tantalum oxide on silica, we first do an aldol condensation to make the C12 dimer. And that is very short-lived and goes on in the same pot to do a Michaels condensation to make the trimer. And once you've gotten to the trimer, this is self-limiting chemistry. It doesn't go on to make the tetramer and pentamer and so forth. And we can get two classes of compounds. We'll either get the cyclohexenones, so there's the cyclohexenone ring, or we'll get a benzene ring in the middle. And the rest of the chemistry is in the form of these side branches. So we have mostly worked to date on the cyclohexenone compounds, and we transform those into hydrocarbons by doing hydrogenation at mild conditions with platinum on niobium phosphate. And this takes out the oxygen. First goes to a OH group, and then that's knocked out, and the double bond is saturated. So you end up with these cyclohexyl derivatives that have 4 branches on them. Now what's attractive is I don't have to do this with individual 2 ketones. I can do it with a mixture of ketones. And the oligomerization is random. So I can actually put into the pot a prescribed mixture of various ketones and predict based on statistics what I'm going to get out. So on the left, I'm showing you here in panel A what would happen if you took roughly equivalent amounts of butanone, pentanone, and heptanone and reacted them over this calcined hydrotalcite to produce the product distribution I'm showing you here. And that has the range of materials that you would like for jet fuel. And in fact, the simulated boiling point curve here, which I have the cursor on, is exactly what you would expect for jet fuel. If I add heptanone to the pot and do this again, I'll get the blue distribution, which now goes out to C21, and it has a somewhat higher boiling point curve, and this is representative of diesel fuel. So I can make jet or diesel by tuning what you put into the pot in the way of these synthons. And these materials have been tested out by BP, the sponsor for our work, in their own laboratories and found to be good quality fuels. They have all the right characteristics. And I want to point out that this work has just come out in 2 papers, one in ChemSys Chem, and last Monday there was an online issue in PNAS of an overview paper. Now, by making the tail on the ketone longer, we can do the same thing, but now push the products into the lubricant range. And I'm showing you just a few examples here in the table, and in particular I'd like you to look at the one where we start with the C11 ketone, and now we're working with a single material, not a mixture. And this makes a C33 lubricant with this viscosity at 100 degrees, this viscosity at 40 degrees, a viscosity index of 123, 4 point of minus 69 C, an oxidation temperature, this is where oxidation starts, 226, and the TGA NOAC, which is a metric of volatility of 2.58. Now what I'd like you to compare it with is the line here, the row in red. So this is today's synthetic polyalpha olefin lubricant that you can buy. This is the base oil. And you can see that we're a little bit high at 100 degrees here, and also at 40 degrees on the absolute viscosity, but the viscosity index is right on. We're essentially at the desired pour point. The DSC oxidation temperature is equivalent, and we're better on volatility. And we now know how to tune these compounds so we can move our way from the C33 range into the desired range so we can mimic the lubricant. So this is a very attractive approach. And these materials are high value added materials. They sell for something like $3,000 a ton. And so BP is quite interested in this as maybe a first way to commercialize the conversion of biomass to a product. So to summarize to this point, we're taking sugarcane, converting it to sucrose, and from the bagasse extracting the xylose, doing acetone, butanol, ethanol fermentation, and doing the dehydration of the xylose to make furfural. Now the question is, can the proposed scheme be done with a small greenhouse gas, GHG, footprint? This is, remember, one of the critical questions I posed at the beginning of the lecture. And to do this, we've done a life cycle analysis on this hypothesized biorefinery sitting in Brazil. And so we start here at the top. I know this is hard to read, but it's you can see the plot in the PNAS paper that has just come out. Start here with taking into account the fertilizers and chemicals needed to grow the sugarcane. Here's the sugarcane supply, the diesel to run the tractors, cane milling, pre-treatment, and from the cane milling then we extract the sucrose, which is fermented to make butanol, acetone, and ethanol. Part of the ethanol is then used in steam reforming to generate hydrogen. So this is how we generate hydrogen in a green way. So we throw away the carbon as CO2, but it's green since it came from the atmosphere. The pretreatment of the bagasse led to the pentoses, which are then dehydrated to make furfural. Now, the remainder of the bagasse is about 75% of that material is used for process heat and also to generate electricity. And this is already current practice in Brazil, which is to take part of the bagasse and generate electricity and put it on the electrical grid. And so this plant would take advantage of that and take this as a credit. Now, I won't lead you through all the processes at the bottom here in the middle, but at the end of the day, you make jet fuel, you make lubricant, more jet fuel, more lubricant, and jet fuel. So what has been done in this LCA analysis is to look at the pluses and minuses of each one of the steps as you trickle from the top to the bottom, and then to look at three scenarios. One which maximizes the reduction of greenhouse gases, that's A. B is maximizing the jet fuel production. And C is maximizing the lubricant production. Now you can see that the first and the third units here end up with the smallest amount of greenhouse gas emissions. Now our reference point is 90 grams of CO2 equivalent per megajoule of energy content in the final product. And by the way, when you think of lubricants and where they're going, eventually they get burned up. So that's why we look at it this way. So what we're saying is that the processes, schemes A and C, will take you from 90 down to 18, or an 82% savings in greenhouse gas emissions. We could also do some other things, and I'm going to end the presentation with a few more slides here. We could start with an alcohol, say butanol, dehydrogenate it to make butyraldehyde, or butanal, do aldol condensation, and then take the hydrogen generated in the first step and replace it to make this branched alcohol. It looks like a Gerbet alcohol. And in the case of butanol, this would be a C8 alcohol. And in fact, there's a patent on this type of product. And it's a wonderful diesel additive because it adds cetane number to the base diesel. So what we're going to ask is, can we do this heterogeneously? So we'll see that we can first do the dehydration very effectively, and then the aldol condensation. So we've looked at metal nanoparticles on hydrocalcite as our catalyst. And we see that in particular we can do the the dehydrogenation of butanal to butyraldehyde with 90% selectivity and virtually 100% if you consider that the remaining product is 2-ethylhexanol, which is the condensation product. So this is a very effective catalyst. We can push up the conversion to higher levels with very little loss in selectivity, and this is a very durable catalyst. So gold nanoparticles on hydrocalcite are very effective in doing this first step. Now we want to do the second step shown here in the box, which is the aldol condensation. And for this, we have found that an effective catalyst is one which is what is called an organo catalyst. So it involves this alkyl amine. It's actually a secondary amine as shown here. And an acid group, which on the support could be the native silanol, or we could replace that with tin, zirconium, titanium, or aluminum atoms. So we can change that metal OH structure. So we have an acid-base pair. And we have found that if you make the base a secondary amine, it's very active, as shown here by the bar chart, compared to primary or tertiary amine. And then if you tune the acidity of the OH group, going from silicon to aluminum, you lower the activation barrier for the process and you increase the turnover frequency under identical conditions. And so using this method, we have essentially 100% selectivity to the desired dimerization product, and we make this 2-ethylhexanol at the end of the day with the hydrogenation using the hydrogen that was released in the first step of dehydrogenation. Now, more recently, we have found that the same catalyst, but tuned on the amine side, can also do ketone dimerization. And this is illustrated schematically here with the 2-hexanone going to this dimer product. So one thing you can do with this dimer product is readily hydrogenate it, get rid of the double bond, and get rid of the oxygen there, take that out as water. And now you have a branched C12 alkane, which is right in the middle of either jet or diesel. You can use it either way. So now, by tuning this hexanol, making it longer, we can make other compounds, including things that are in the lubricant range. For example, if we started with a C15 or a C16 ketone here, we could readily make things in the lubricant range, which are completely like today's lubricants. So the whole point here has been to show you how flexible the chemistry is. If you start with sugars and move towards things that are essentially hydrocarbons, I've shown you that the dehydration of xylose and glucose can be done with up to 85% selectivity. It requires a combination of Lewis and Bronsted acids. They can be homogeneous or heterogeneous. You can get rid of the product by separate the product out from the aqueous phase readily by using a solvent. This is liquid-liquid extraction, LLE. Or, and I haven't shown this, we are now working on some evaporation membranes, which will do this effectively. Then I've shown you that you can take the furfural and 5-HMF to fuels and lubricants by a variety of processes. The net point is that this is a greener process, at least as envisioned. We don't know yet the full economics. That's another important thing to be looked at, and that's in the industrial sector. And then finally, I've shown you that you can take individual alcohols. It's not limited to butanol. You can do this with ethanol, propanol, butanol, the ones we've looked at so far, and do dehydrogenation to make the alkanals. You can then dimerize the alkanals to fuels and possibly to lubricants. So it requires me now to come to an end, and I just want to thank the young people who did all of this work and point out in particular Corinne Scown, who is a staff member at the Lawrence Berkeley National Laboratory, and she is the one who did the LCA analysis And we feel very strongly now that this is the kind of thing that should be done on any kind of biomass conversion process. One should look at what are the consequences of conceiving a full process in terms of the greenhouse gas emissions. This work was supported by BP through the Energy Biosciences Institute, and it is work that is ongoing for the next 5 years. So with that, thank you very much, and I'll be happy to answer any questions.
Okay, we do have some time for questions or discussion. Yes.
I'm Robson Montero from CBMM. My question is regarding the niobium phosphate support that you use for the hydrogenation. Is there any special role of the support for the hydrogenation?
Oh, for that? Okay.
The niobium phosphate.
Yeah, so the hydrogenate, we have two kinds of supports that we like. One is carbon. It's completely innocuous in the presence of sugars and other oxygenated compounds. And this is great if you want to do hydrogenation of double bonds, particularly if you use palladium. If you want to open up oxygen, take oxygen out of tetrahydrofuranic rings, then it's desirable to have an acidic, Lewis acidic support, and niobium phosphate is the best one we've found so far.
Other questions? Try it now.
Okay. Michiel again, Delft University. Thank you for your presentation. Can you say something about your stability of your catalyst in your processes?
The acoustics here are very poor. I can't understand you. I can hear your voice, but I can't understand.
Can you say something about the stability of the catalyst?
Yes. Yeah. So the question is, can I say anything about the stability and recyclability of the catalysts? Yes, all of the catalysts that we have used are stable out to roughly 60 hours, which is the length of time that we have tested them. I know that this is short on an industrial scale, but this is a reasonable time scale for graduate students and postdocs. Now, I will say that the calcined hydrotalcite slowly does deactivate in the presence of water. This is well known in the literature. But we've recently found ways to make a material that has the chemical and catalytic characteristics of hydrotalcite. It isn't hydrotalcite anymore, bulk in the sense, but it is now stable in water. And I can't say more than that.
One more question.
Sure.
What about your separations?
Okay. So the one separation I talked about was getting the furanics out of the water. That works extremely well, and we can tune that. The other separations that are in this block diagram, we haven't worked on, and we probably won't because we have only limited funding and it's focused on catalysis. But these are our industrial partners. BP have their own engineers looking at that, and they conceive these as being feasible separations. Cost, I don't know. We'll see.
Okay. One final question.
Thank you for your presentation. This is focusing on the production of fuels, but is there the possibility of focusing on the production of other chemical products of higher aggregated value?
Okay, so the question is, are we focusing also on making chemicals? In the initial round, the answer is no, because that's not what our sponsor wanted us to do. They wanted us to focus on fuels and lubricants. But now the perspective within BP is changing, and so we are looking at making monomers for certain polymers, replacements of things that you would find in the water bottles we all carry around, or juice bottles, okay, PET. And we have some successful first starts in that area and things that they might even patent.
Okay, with that, we need to conclude the discussion of this talk. And thank you, Alex, for a wonderful talk.